Okay, so this next problem also works on the force, but this time we use the force on a current. So a force on a current carrying wire is the current times the length of the wire times the magnetic field times sine of theta instead of QVB sine theta. And so what we have is we have a copper rod that's lying horizontally in the plus x direction. It carries a current of 11 amps. This is my current in the plus x direction, so it's going like that. The length of the rod is 0.45 meters. And I'm told the mass of the rod is 0.17 kilograms. And what I want to know is what's the size and what's the direction of a minimum of the magnetic field that's needed to levitate the rod, so to make the rod float. So what's going on in that case? Well, what we know is from, let's see, what was it, chapter 4 in physics 1, that there's always a weight, force mg downwards. And in this case, we're going to have a magnetic force. It's called force magnetic upwards. So force magnetic, that's my equation ILB sine theta. And if it's going to levitate, what we need to do is we need to balance the field and the weight so that they're equal and opposite to each other. So what I want is let me write it like this first, magnetic force is equal to mg. So what I want is ILB sine theta is equal to mg. All right, so if I look at my problem, I know my L. So let me write them down. Again, mine out all my data from there. So I've got L is equal to 0.45 meters. M, the mass, is 0.17 kilograms. I've got a current, I, is 11 amps. And I'm asked what's the magnetic field and what's the direction of the magnetic field. Okay, so that's going to be theta. All right, so I've got, let me go to a different color. I've got I, I've got L, I've got M. G we know is 9.8. That's just a constant for physics 1, meters per second squared. Okay, so I've got everything except B and sine theta. All right, so what are we going to pick for sine theta? Well, we want the minimum, the smallest amount of magnetic field. So that means we want sine theta to be its biggest. And so that means theta is going to be equal to 90 degrees. So my magnetic field is going to be either into or out of the page. Okay, remember we have to use the right-hand rule. So if I want my force, the magnetic force, to be upwards, take your right hand, put the fingers in the direction of the current. Okay, so you're going to take your palm. So let me go like this. So here's your hand. Oops. You want your thumb to be pointing in the direction of the force. And you want your fingers, there we go, 4 fingers. So you want your fingers pointing in the direction of I, your thumb pointing in the direction of the field. So I have the current. No, I'll get it right eventually. You want your thumb pointing in the direction of the force. So your thumb points in the direction of the force. Your fingers point in the direction of the field. So your palm is the direction of the field. So the direction of the field, which means your palm is pointing into the page. So the magnetic field must be going in, so I can make an X symbol. Remember that X symbol means into the page. All right, so we've got the direction. So we want theta is 90 degrees. So now I've got that. So now I'm just going to get B. B is equal to mg over I L sine theta. I know all my numbers, so I can just now plug and chug. So B is equal to the mass, 0.17, times G, 9.8, over I, 11 amps. The length is 0.45 meters, and sine of 90, which is 1. And I get 0.337. And let's see, all my numbers have 2 significant figures, so I need to round that to 0.34, and the units are Tesla. So 0.34 Tesla into the page. If the magnetic field were coming out of the page, and if you rearrange your hand so that your palm was coming out of the page and your fingers are still pointing over in the plus X direction towards the right, you'd find that your thumb is going downwards. So that would make a force that would reinforce the gravity, and then the wire would sink down to the ground very quickly.